Okay, so let's move to next one. The next speaker is Kashi from Institute of Photonic Integration, IPI, Eindhoven University of Technology in the Netherlands. So the topic is about electro-optical slot waveguide phase modulator in the IMOS platform. Yeah, please.
Hi, everybody. Good morning. Welcome to my talk. My name is Amir Abbas Kashi, and I'm a PhD student at Technical University of Eindhoven. And my talk today is about electro-optic slot waveguide phase modulator in IMOS platform. The outline of this talk is first we say some word about the motivation of this work, and then I introduce IMOS platform, and then I say some word about a slot waveguide phase modulator and working principle of these modulators. And then I present the measurements and the result obtained from these measurements, and then I conclude my talk. Communication, we are all connected to each other nowadays, and we send and receive different type of data, and we have this growth in data traffic every day, and data centers as they have to come up and keep up with this increasing data traffic rate. And one of the key components to look after to satisfy this increasing demand is to look after optical modulators. Optical modulators need to be fast, small, and very energy efficient. And one of the very good candidates to satisfy all of these requirements is the semiconductor hybrid phase modulators, which are a slot phase modulator is belong to this category of the modulators. And IMOS platform is one of good platforms to realize such a device. IMOS simply stands for indium phosphide membrane on silicon substrate. So you see in the cartoon, we have this indium phosphide membrane as our optical domain. And then we have this silicon carrier for having the electronic counterparts of the optical components. With this platform, we can go to very high density integration thanks to the high refractive index contrast of the platform. And then also we have full photonic functionality, which means that we can realize both active and passive components in this platform. And also we have possibility to use both sides of the optical membrane. And then we have, as I said, we have possibility to integrate electronic counterparts of the optical components in the silicon wafer. And if I want to explain how the slot waveguide phase modulators are working, we have to look at the cross section of these modulators. You see in this figure, the cross section of this modulator. It is simply two narrow indium phosphide waveguides running along each other with a gap in between, which is called a slot. And these waveguides are electrically connected to the metal pad with a very high doped layer of indium phosphide, which is called a slab. And our electro-optic polymer is existing in the slot region. And if we look at the electric field distribution profile of the optical mode, we have high intensity of the optical mode in the slot, where we have our electro-optic polymer also. And if we apply electric field to this slot, thanks to the Pockels effect of the electro-optic polymer, we can induce a phase shift, which is coming from the change in the refractive index of the electro-optic polymer. And the change of the refractive index following this formula, and the important parameters in this formula is the R33 value, which is the electro-optic coefficient of the polymer, and gamma, which is the confinement factor of the optical mode in the slot, which is around 30% for regular configuration. And if we want to look at how to realize these devices on IMOS platform, this is the schematic cartoon for the chip. And here we have GSG pads for the electrical signal. And then for the optical input, we use these surface grating couplers, and the light will couple through this coupler and then travel through the waveguides and then split to two arms of this Mach-Zehnder modulator, and then travel through this slot and then combine again from two arms, and then we can take out the optical signal from other surface grating coupler at the other end of the chip. And if we want to look at the fabricated sample, you see the optical image of this fabricated sample here. The footprint of this sample is 300 micrometer by 600 micrometer. And if we zoom at this rectangular area, we see very clear definition of the slot with the waveguides around it. For characterization of these devices, normally for optical modulators, optical phase modulators, we use DC characterization, but because of the charge screening effect of the electro-optic polymers, we have to use low frequency characterization method. And for this measurement, we have this setup. We have an external tunable laser. Then we have this polarization controller to control the polarization of the light, and then couple the light into the chip and take out the light out of the chip, and then send it to a photodiode and measure the voltage of this photodiode in an oscilloscope. And the signal, electrical signal, is applied with this signal generator to the GSG pad. And the specification of the sample under test is a symmetry Mach-Zehnder modulator with the arm length of 500 micrometer and a slot width of 100 nanometer. And if we do this measurement, we obtain this result. And you see from these measurements, we obtain a V pi voltage of 9 volts. And if we calculate V pi L pi, which is showing the modulation efficiency of the modulator, it's 4.5 volts millimeter, which is a good number in this kind of modulator. But the R33 value of the electro-optic polymer is a bit low. It's 11.5 picometer per volt, which is coming from the poling condition of the polymer. And there is a room to study how to increase this number, and it can increase also to 100, 200 picometer per volt. And extinction ratio of this device is 10.6 dB. After knowing the V pi and working DC point of the device, then it is time to do measurement of high frequency electrical RF measurements. And the setup for this measurement is simply we use a VNA, and then we launch the high frequency electrical signal to the GSG pad of the device, and then we read out the signal from other end of the pad. And if we do the measurements, we have S parameters of the device. And if we plot the S21 parameter, which is showing the ratio of the output to the input, it is in the blue curve, you see the measured data, and in the red curve, you see the equivalent electrical circuit model data. And they are almost matching each other, and they are in a good agreement. And the model could predict the performance of the device in this case. And the 6 dB electrical bandwidth is beyond 25 gigahertz, as you see here. So this device electrically performing very well. And other important parameters to measure is the loss, propagation loss, which is here we demonstrated dB per centimeter. You see the graph here. And other important parameter is the characteristic impedance of the transmission line. And it is around 35 ohm in the range of frequency. And also here you see the model is predicting very well the behavior of the device here. So the equivalent electrical circuit model is validated. So then further we can use that model to predict some behavior of the device. After knowing the performance of the device electrically, it is time to do the electrical optical measurement. And for that, we use this setup. So we have, again, external tunable laser, then polarization controller. then launching the light through the device, and then collecting the light out of the chip and feed it to the EDFA to amplify the signal and pass it through a bandpass filter, and then again feed it to a VNA. And electrical signal also is applied via this VNA with a GSG pad, and then going through the device and terminate with a DC block and a 50 ohm termination. If we do that measurement, also we get this electro-optic response in dB versus frequency, and the measured 3 dB optical bandwidth of the device is 11 gigahertz, and from the model it's 11.5. Again, the model is predicting the behavior of the device well until the range of the frequency that we are studying it. And if we want to improve this 3 dB optical bandwidth, there are some ways that we studied through the model. So one way is changing the doping concentration of the high doped layer of the slab that I mentioned earlier. So if we increase the doping level from 1 times 10 to the 17 to 2 times 10 to the 18 per cubic centimeter, you see the 3 dB bandwidth of this device can increase drastically over 30 gigahertz. And another way to improve this 3 dB bandwidth is the slot width. And if we go from 100 nanometer to 400 nanometer of the dimension, then this 3 dB bandwidth is also increasing drastically to over around 30 gigahertz. And we can also combine these two factors to get better performance. With this, I conclude my talk. And in this talk, I demonstrated for the first time a slot waveguide phase modulator on indium phosphide membrane with 11 gigahertz optical 3 dB bandwidth, and V pi L pi equal to 4.5 volt millimeter. And as I said, for the future works, we can work on the polling condition to increase the polling efficiency of this EO polymer to get a lower V pi value. And also we can work on the doping concentration to increase this 3 dB optical bandwidth. With this, I thank you for listening to my presentation, and I appreciate if there is any question.
Okay, thank you very much. So there is a question for you. How accurate is your measured R33 and the measured V pi and the
Let me just I'm just trying
okay,
to get
the first one. Yeah, how about the question from the audience is how accurate is your measured gamma 33, the coefficient actually?
Yes, the accuracy depends. So this R33 value is coming from this equation, and here we have everything except this confinement factor, and this confinement factor is coming from the simulation. If we assume that is accurate, then we say this R33 value is accurate. So accuracy depends on the accuracy in this confinement factor.
Okay, so one more question from the audience. Is the MZM configured to a push-pull operation, or is the electrical signal applied to only one of the magnetic arms?
No, it is on push-pull configuration.
Push-pull, okay. Okay, so one more is has there been some study on beam work-off between RF and the optical wave?
Yes, actually, this is something that I'm currently looking at. Yes, there is because you see from the electrical measurement, the bandwidth is beyond 25 gigahertz. And then for the optical, we see this limitation, and it is coming for different parameters, different factors influencing this, which one is walk-off. And I'm currently looking at this.
Okay, thank you very much.
Welcome. And